Welcome to Dr. Nakamura's lecture series on Advanced Bridge Engineering. Number B-2.2. In the previous video, I presented Part 1. Now, Part 2. I found another wobbly footbridge. M-bridge, a suspension footbridge in Japan where the lateral vibration occurred. This is the M-bridge, suspension bridge with a main span of 320 meters. It is situated in a scenic place in Japan. The deck is only 2 meters wide. It's a long and narrow bridge again. This is what happened. As you can see, the girder vibrates in the lateral direction. It is much larger than the T-bridge. Also, the vibration mode is different in a strange way. Some people feel uncomfortable. I want to find its mechanism of this vibration. I attached the accelerometers at 5 positions. Span length L/8, L/4, 3L/8, L/2 is the center, and 9L/16. In addition, the accelerometer was attached to the pedestrian. Its data was transferred by telemetry link to the PC at the end. We found that pedestrians synchronized to walk on the T-bridge, but the interaction between pedestrians and the girder movement was not clarified. That's why the accelerometer was attached to the pedestrian. All the measured data were collected and stored in the data logger and the PC. This is the accelerometer attached to the girder. This is a person equipped with accelerometers and antenna. The accelerometers are attached on the waist belt to measure the vertical and lateral movements. The equipped monitor person walked among other pedestrians, and its acceleration data was sent by telemetry link. These 5 figures show the girder lateral displacement at the measured positions when the test person walked at L/4, the quarter span position. B shows the data at the quarter position, which is a clear sinusoidal wave. Other data A, C, D, E at other positions also show periodical movements. These data were analyzed to get the power spectrum. All the power spectrum have a sharp peak at 0.88 Hz, which is also close to the walking frequency of 1.0 Hz. Therefore, this vibration occurred on the M-bridge has the same mechanism as the T-bridge. This shows the mode shape of the third asymmetric mode analyzed by FEM. The square marks indicates measured displacements at 5 positions. They correspond to the analyzed shape. Now we found that the girder vibrated in the third asymmetric mode. This shows the lateral displacements of the girder and the monitored pedestrian at the quarter span position. It is seen that both have the sinusoidal curves with the same frequency, and so the pedestrian synchronized to the girder. However, there is a time lag between two lines. As for the phase, the pedestrian is ahead 120 to 160 degrees of the girder. This was a new finding. This shows the lateral displacement at the peak of the vibration, where the maximum amplitude is 45 millimeters. As you can see, two lines is tuned and not tuned in turn. This means the pedestrian partially synchronized to the girder. The bridge is open at 8 a.m. These are the lateral girder displacements at two positions just before 8 a.m. There was nobody on the bridge, so this is the ambient vibration, which was very small. You cannot understand by only these data. Then the power spectrum was calculated. They have a sharp peak at 0.27 Hz, which corresponds to the first symmetric mode. These are the first, second, and third symmetric modes in the lateral direction. The girder vibrated in the first mode when nobody on the bridge. Just after 8 a.m., two people came and crossed the bridge. Still, the amplitude is very small. However, the power spectrum is totally different. There is a sharp peak at 0.88 Hz, which corresponds to the third asymmetric mode. Only two people changed the dynamic behavior of this 320-meter long bridge. It's very interesting. These are the three asymmetric modes. That's for your reference. The third mode has a natural frequency of 0.88 Hz, which is the lateral vibration occurred on the bridge. Now part 3. Design factors to affect the girder response. I wanted to find a method to estimate the response caused by pedestrians. It would be helpful when you design a footbridge. The response induced by people depends on pedestrian density, mass of the girder, its structural damping, natural frequency of the girder, and rate of synchronized pedestrians. I tried to establish the equation to predict the girder response of bridges with different forms and dimensions. This is the dynamic model for this problem using modal analysis. I assume a single degree of freedom dynamic model using the modal analysis of the first lateral mode because the girder vibrates with only a specific mode. The model consists of bridge modal mass mb, modal stiffness kb, and modal bridge damping ratio cb, to which the modal pedestrian force Fp is applied. This Fp is very complicated and the key of this model. This is my proposed equation. A is the modal dynamic equation of the single degree of freedom model. Xb is the modal lateral displacement of the girder. Fp is the external force induced by pedestrians. B is Fp, which is assumed to be proportional to the modal self-weight of pedestrians, mpg, multiplied by two coefficients k1 and k2 and two functions h and g. Coefficient k1 is the ratio of the lateral force to the pedestrian's weight and is assumed to be 0.04. The coefficient K2 is the percentage of pedestrians who synchronize to the gather vibration. H is a function to describe the pedestrian's synchronization nature. It is assumed that the pedestrians synchronize proportionally with the gather velocity xb' at low velocities. When the gather velocity becomes large, the pedestrians feel uncomfortable or unsafe, and they decrease their walking pace. Therefore, the gather response does not increase infinitely, but saturate at a certain level. G is a function to describe how pedestrians synchronize with the bridge natural frequency. Obviously, the pedestrians are most likely to synchronize at the bridge frequency around 1 Hz. This shows Fp with the gather velocity. Fp increases proportionally with the gather velocity at the low velocity. However, when the gather velocity becomes large, the pedestrians decrease their walking pace and Fp saturates. This is the measured data of the T-bridge. And this is the simulated results. These values were chosen for this vibration case. dP is the density of pedestrians. The increasing process and the maximum response reasonably agree and validates my proposed equation. This shows the lateral gather displacement xb with the density of pedestrians dP, calculated by my method. You understand, more people increase the gather response. This shows the calculated lateral gather displacement with the gather mass per unit area. Clearly, lighter gather increases the gather response. Nowadays, some bridges are slender and very light because of the aesthetic reason or using new materials. In such a bridge, countermeasures to suppress the vibration would be necessary. This shows the calculated lateral gather displacement with the bridge damping ratio zeta. Smaller damping increases the gather response. It is not easy to predict bridge damping in the design stage. In general, slender and light bridges have low damping. When you design such a bridge, be careful. This is a comparison of measurements and simulation. The lateral gather displacements of the T-bridge and M-bridge are shown with the two predicted lines for the damping ratio zeta of 0.006 and 0.008. There is a reasonably good agreement. This is the Solferino Bridge in Paris, which also suffered the lateral vibration. My study has been followed by many researchers in the world, and now the lateral vibration becomes a major topic. I wanted to show my past studies to particularly young engineers, because you will surely encounter unexpected problems in the future. In such a case, please recall how I tackled a difficult and new problem. Thank you, and see you next lecture.